All right, so we'll begin with lecture number 5, I believe, on weak form Galerkin. And now for real, we're really talking about now much closer to finite elements. We've gotten a lot closer to finite elements now. So this is really where we're going to focus a lot of our time moving forward. So that's why this lecture becomes so important for you guys to really develop a sound understanding of the concepts I'll be trying to transfer to you today. Okay, so in the previous lecture we talked about an approximation method. What was that approximation method that we discussed? Strong form Galerkin. Strong form Galerkin. And in strong form Galerkin, I am going to use a method to approximate the solution to the partial differential equation. And the approximation solution I select must satisfy what kinds of boundary conditions? Not 261A, somebody else. What kinds of boundary conditions I must satisfy for essential and natural boundary conditions? What kinds of boundary conditions I can have in a partial differential equation? There's two types of boundary conditions. What are those two types? Essential and natural. So what kinds of boundary conditions I need to satisfy for strong form Galerkin? Remember, strong form Galerkin must be true at every point in the domain. So it must be satisfied, very good, all the essential and natural boundary conditions of the problem. I really need you guys to review these materials. Today we're going to go very heavy into weak form Galerkin. And on Thursday I'll be covering Riley-Ritz. And then the homework will be about all three. Strong form Galerkin, weak form Galerkin, and Riley-Ritz. You're going to solve the same problem 3 different ways. And so it's very important for us to not just do the homework you're working on now. You'll have to multitask. Do that, plus continue to study the materials that we have at hand. Okay? Very, very important. Any questions on the audience? Any questions? Okay. I went through 5 examples. Today I'll go through 6 examples when it comes to weak form Galerkin. Now it sounds very, very complex. Weak form Galerkin. You don't have to worry about it. It's just the name of the method. Okay. With strong form Galerkin, can somebody describe for me what were the steps required to approximate the solution for strong form Galerkin? What were the steps?
Yeah,
please.
You pick some weighted functions, and then you make sure that your approximation functions satisfy the boundary conditions.
And so basically what you're saying is I multiply the partial differential equation by a weight function, and what I think we need to say next is that we need to form the weighted residual, which is to integrate that multiplication of the partial differential equation, which is you're going to construct a residual function, right? Remember?
Yeah.
Times the weighted function, integrate that over the domain, and then select a suitable, which I call admissible, approximate solution to the problem. And this approximation method will be inserted into the residual. And I'll select the weight functions to be equal to the basis functions. I'll make the residual orthogonal to each of the basis functions, and I'll get n equations, n unknowns, and then I can now solve for the coefficients. And now there's about 4 to 5 different guidelines of what this approximation method's approximate solution must satisfy. So it needs to satisfy essential and natural boundary conditions. It must be sufficiently differentiable. Right, so my residual function does not cancel out to 0, right? It needs to be sufficiently smooth so I can take derivatives, right? So we discussed all these things, right? So hopefully you've gone through some of that. And today, the 3 methods are strong form Galerkin, which I already covered. We'll be moving to weak form Galerkin today. That's the lecture for today, which is really the method for which finite elements is based on, directly on that. So it's very important for us to really understand this lecture today. Okay? So the main idea in strong form Galerkin, I take the partial differential equation, I form the residual, which is R, is given here as R, and I'll form the weighted residual, so I'll take the residual times the weight function, and I'll make it orthogonal. Okay, so this is what we call the weighted residual right here. Okay, and then we'll select an approximation function for the primary variable of interest. The primary variable of interest is W. That's what I'm trying to solve for. So I'll plug that in here. But then for the weight function here, I'll select the basis function. So I'll make the residual orthogonal to each of the basis functions. And there's n of them. Phi1, Phi2, Phi3. Phi sub 0 is not a basis function. Phi sub 0 is only purpose in life is to satisfy the non-homogeneous form of the essential and natural boundary conditions. And so we went through this example, we substituted that in, and then we selected for the weight function, we selected phi1 up to phi n, and we have n equations, c's, n c's, so solve for c1, c2 through cn. That was the idea there. But the issue with the challenges we talked about in strong form Galerkin is that the approximation function in strong form Galerkin must be sufficiently differentiable. And in the case of a polynomial, in the example that we just went through, it will have to be up to an order, what order polynomial, for me to survive these differentiations. What order polynomial can I have here? Minimum. Fourth order, very good. So I actually made a purposeful mistake here to see who may catch it. I said third order polynomial to see if you're awake. I wanted to misguide you, but she didn't fall for it. Very good. So fourth order polynomial, and the approximation function must satisfy all boundary conditions, essential and natural. But the problem is that it will be very difficult to select an approximation function and make sure that it also satisfies natural boundary conditions. For this problem, it's easy. It was easy and doable. But say for an airplane or an aircraft, if I need to also satisfy boundary conditions that are natural, it will be very difficult to do that in a finite element scheme. Okay? Another example is the example of a heat transfer problem. In a heat transfer problem, in an orthotropic composite material, I'll have two conductivities, single equation, the only unknown is temperature, and I'll again construct the weighted residual. I'll take this equation, multiply it by V, the weighted function, integrate it over the domain, and that's my weighted residual. Same process, okay? But now, I'll also take the temperature, approximate it over, approximate the solution to the problem, and this is the way it's going to look like. Maybe I will have a polynomial, sine, cosine function, and I'll substitute this temperature field that's approximated into the weighted residual, and then I'll take this weighted residual function, make it orthogonal to each of the weight functions which have been selected to be the basis function. And if I do that, now I'll have n equations, n unknowns. Okay? But in this example, we do have another issue. So what if I want to have a linear approximation? I don't want to have a quadratic approximation for temperature. What's going to happen here if I use a linear formula for temperature approximation? What happens?
Can't use it.
Sorry?
Can't use it.
Well, I could use it, but what will happen? Then I'll get 0, right? All this will go to 0. That's not desirable. I don't want that, because then I'll have plus Q. This will never be equal to 0, right? Except if phi is 0, and that's not going to give me the coefficients that I need. So it needs to be sufficiently differentiable. It needs to satisfy the essential and natural boundary conditions. And so it is a challenging problem this way. But instead, if we approach the problem a little bit different and think out of the box, maybe we can get to an approach that's powerful, and it will impose less restrictions in what needs to be done. Okay? And so to do that, I'll lay out the blueprint for you, step by step. Hopefully you will follow it. Okay? But what we're going to do is do the same thing. We'll form the residual first. We'll then form the weighted residual. Make the weighted residual. We'll make the residual orthogonal to the weighted function, same way. But here's the trick. What we're going to do is that we're going to lower the continuity requirements, right? So in here, up to what order polynomial can I survive this? It has to be fourth order. But if I have a way of lowering this differentiation to a lower order, say I can get it down to second order, that'll be actually really nice, because then I can use a polynomial of what order? Second order, right? Then I can use a quadratic approximation. That'll be great. And in a temperature example, if I go back, in this temperature example, what if I can make this from 2 down to 1? Can I use a linear approximation now? Yes, I can. And so what we're going to try to do right now is I'll basically lower the continuity requirements here by using a trick, and it's called integration by parts. I'm going to integrate by parts to transfer this differentiation onto the weight function. So I'm going to transfer these two derivatives into the weight function, and that way I have 2 of them here in W and then 2 of them here, and that way now I have lowered the continuity requirements. And by doing so, by lowering the requirements, I basically have weakened the continuity requirements. That's why it's called a weak form Galerkin. I'm postulating a formulation that has weakened the continuity requirements. Okay? And so in school, they probably taught you this formula, right? How to integrate by parts. And you can use this approach. You can go back to calculus book and revisit this so you can remember how to do this integration by parts, which is really basically the chain rule, in essence, or multiplication rule of differentiation, but in reverse, right? But instead, I'm going to show you a different way that I think helps to do it quicker for a lot of different problems. But it's up to you which method you select. So you can select this method, or you can select the next method I'll be showing you in the next slide, okay? But what we're going to do, the goal, and hear me very carefully, the goal here is to lower the continuity requirements. So I want to take 2 of these differentiations and bring them over. I want to bring 2 of these over. That's my goal. Because that way, I can split the order from 4th to 2nd order. So if I have a 6th order differential equation, I will take 3 of them, put them over here. 3 of these derivatives over. If you have an odd derivative, say you have 3 derivatives instead of 4, 3 of them, you can split that by half. But you can do your best. In essence, you split them as best as you can. And the idea is to get it in half the best way you can. That's the idea here. So the way to go about this is that I'll take this term, which has a differentiation. The Q doesn't have it, but don't forget it. That's number one source of error that I see is people forget that they had the Q originally. And what you're going to do, you're going to put the V on the left-hand side, and you'll put the remaining part here, the one here that multiplies V, you're going to put it on the right-hand side. And so what you're going to do, this is just very mechanical, okay, very mechanical, but I do encourage you to go through these steps so you can see it does work out, I did it like 15 years ago, so I haven't repeated it again. But I do encourage you to go through those steps. In essence, you will take 1 off every time. So I took 1 off and then 1 off. And now I'm left from 4th order to what order? 2nd order. I stop right there. Don't go further. That's what I want. That's exactly what I want. I want to split it in half, the order of differentiation. And then for V, what I really want to do is transfer these primes over. So what I'll do is increase the primes 1 order at a time. And you'll write them down just like I did. And then you'll draw alternating arrows going from plus, minus, plus. So I'll have a plus going diagonally down, minus, and then plus. Okay? And you'll draw an arrow just like I did, plus, just like that. Okay? The bottom arrow, the one that goes from the right to the left, will go back into the integral. Just like you see here, it goes back in there. And then don't forget this minus q. Bring it over. Okay? Now this minus q is times v, so that's how it goes. And the one here is just ei w double prime times v double prime. You bring it right there. All right? And so that's what goes inside that integral. And what I'll do next, I'll multiply the diagonals. And I have two of them. I have one here and then one there. Okay? When you integrate by parts, I want you to understand physically what you're doing. What you're doing when you're integrating by parts, you are relating the domain, which goes from 0 to L, and the boundary terms from, what are the boundary terms for a 1D domain? What are the boundary terms for a 1D domain? If I go from 0 to L, what are the boundaries of that domain? 0, x equals 0, and x equals L. Okay? And so in the boundary for the 1D domain, what you expect is boundary conditions that are evaluated at x equals 0 and x equals L. So these terms here that I've drawn, plus, minus, these two terms, this multiplied by that, and this multiplied by that, will go into what I call the boundary terms. Okay? So these are boundary condition terms. And very quickly you can see some quite interesting stuff that came out naturally. And if you haven't recognized it yet, I'll guide you through that. But what you have here at the bottom is called the weak form of the problem. This is the weak form of the problem. And it's exciting in many different ways. Right now, it may not be that exciting, but I will show you later on why this is exciting, how this can be exciting. The one thing I want to point out in these calculations is that you want to focus on this V here. Okay? This is what we want to look at. If I give you a partial differential equation, and I want to know what are the essential and natural boundary conditions of the problem, we want to focus on those V's, these V's right here. These V's are going to tell us, are going to give us a clue as to which are the essential boundary conditions of the problem. Earlier in this lecture, maybe last week, I described what kinds of boundary conditions you could have, essential or natural boundary conditions. And I gave you a definition, and I told you, okay, you can have essential and natural boundary conditions. Essential boundary conditions are those that are basically the ones that you prescribe values for the primary variable of interest. The primary variable of interest is W, sure. But if you want to really know what are the essential boundary conditions of the problem, this actually tells you exactly what those are. Okay? Here you can see that I have a V and a V prime, and we're going to focus on that in a couple of minutes. Okay? All right. Any questions so far? This is going to be going deeper and deeper. So if you have any questions, this is a great time to be asking. Does everybody follow these steps? Okay. I have a question in the back.
It's not a question, it's just like, I just want to make sure that you didn't miss multiplying the second and the third term by V again.
So let's see. Leonardo, did I make a mistake? Can you check quickly? I don't know, look, because I'm too close to the subject. It looks good? Okay, so it looks like it's fine. I see everything done correctly. So V times Q is there. This times that is there. This times that is that one. This times that is that one. So I have all the terms included. So the question audience for the video was, did I mess up anywhere? And it looks like it's fine. Okay, great. But if at the end of the class you still have a question, let's discuss it, okay? Here, I didn't read, you have a question.
Can I ask you a question about this?
Absolutely.
Actually, so could we, so we only integrate the first with the dx, and then the other two terms we just evaluate from 0 to L, and we don't integrate that integral as only the
Right, because those correspond to the boundary terms. If you go back to the integration by parts, if you go back here to the way you do it in school, if you integrate by parts, you will see that there's a term that goes inside the integral. And there's another term that's a boundary integral. And so what you're seeing there is that I basically integrated by part twice in one step, really quick. If you were, and that's what I'm encouraging you to go home and integrate by parts old school, just go one at a time, and you'll see you'll get the same answer. Once you feel very comfortable with that method, then don't use this method, use the other one. Well, it's up to you. I have a lot of students that just prefer doing it this way. I prefer this way because I feel I mess up less times this way. But it's really up to you what you want to use, okay? All right, so here's the steps. I just circled it so you can see how they went into the integral. So I'm going to skip that. So two observations I want to make. So this is a weak form right here that we just discussed. And there's two observations. One of them is that I have weakened the continuity requirements. You can see that because if I plug in an approximation function here for W, what order can I go to now? If it's a polynomial, what is the minimum term that I can put in here? Why are you guys struggling? It's two derivatives. What order polynomial can I put in here so it's sufficiently differentiable? Second order. Thank you very much. Quadratic. But earlier, when I have four derivatives for strong form Galerkin, I had to go up to fourth order. So you can see quickly that I've lowered the continuity requirements. I have weakened, and that's why it's called weak form, the continuity requirements. Secondly, I formed an integral here, and this is qualitatively is an average statement of equilibrium, because this is equivalent to that. Really, this is equivalent to that. Okay, mathematically, this I can go from here to here or from here to here. I can do that. In fact, if you can go from here to here, just integrate by parts again, but the other way. Take these primes and put them over. Okay? And you'll see that next Thursday when I do maybe virtual work. I won't do virtual work. I'll do something simpler than virtual work. But you'll see that I can go from here to here or from here to there. They're equivalent, okay, mathematically. But the bottom one here is different in the sense that I have weakened the continuity requirements. And not only that, it's an integral of the domain, which is a weighted average, really. Unlike this one here. This one is true at every point in the domain. This is basically, on average, is satisfied that ODE, that ordinary differential equation. There's a question on the audience. Go ahead.
In the second term, why doesn't that require a third order?
Okay. Let's see. So I have a, so this came straight from these steps here. Multiply this by that, and that has a third order. Multiply this by that, but this doesn't have a third order. Remember to write this out. For the video, the question was why that didn't have a third order. The answer is because you're going to take this term here, remove one derivative at a time.
My question is,
And this is how I constructed it, right?
yeah, don't you have to pick WFG third order because you have a differentiate the second term 3 times?
So to get to this, right, I'll multiply this times that, and I get that, right? So I'm not sure if I follow your equation. This is what you will get if you integrate by parts. Maybe we have another question. We'll discuss at the end, if that's okay.
Professor, you just mentioned weighted average. And what is by weighted average?
Well, I mean, I'm integrating over a domain, right? So the strong form of the problem, right, is true at every point in the domain. But if I integrate it from 0 to L and take the residual function, make it orthogonal to the weight function, now it's true on average or over the domain, right? Because I'm integrating over the domain. That's why. Okay, so, all right. So hopefully I answered your question. If I didn't, please talk to me at the end. But the important thing that I want to mention here is I've weakened the continuity requirements. I went from strong form to weak form. So everybody here in the midterm exam, if I ask you, why is this called weak form, you should be able to tell me. What is the answer to that question? I think I need to hear Chris because I'm not hearing anybody else say anything. So what's the answer to that question?
You weaken the continuity requirements.
We weakened the continuity requirements, okay? All right. And so one thing I want to point out is that, and I mentioned this, how do I know which ones are the essential and which ones are the natural boundary conditions? When you construct the weak form Galerkin, it's going to give you a clue about that. And so what are you going to do? You're going to focus on the V's. Okay? For the V, I'll switch it to W really quick to see. So instead of V, I'll make it W. And if you do that, then you know what, if I have anything specified on this W, that'll make an essential boundary condition. If I make W, for example, 0 at x equals 0, that makes an essential boundary condition. That's V right there. For V prime, again, I focus on the V, and I see a prime. So I'm going to switch this to W, and I have W prime. This quickly tells me that anything specified on W prime becomes an essential boundary condition. So you can quickly identify what is essential, what is a natural boundary condition by constructing the weak form. In fact, it's very impressive because we constructed a weak form, and suddenly you see two things, two very important things. Is that you realize that this is actually, isn't this the moment, the formula for moment? Isn't that incredible that we got moment from integrating by parts? That's the formula for moment. Isn't it incredible that the shear is the derivative of the moment? Remember, shear is derivative of the moment. We derived that in Euler-Bernoulli beam theory. Well, if I make this prime, that's what I have here. Is the derivative of the moment, and that's a shear. So it's very interesting how this came out naturally. I think there is a question in the back. Was it you?
I'm just wondering if we only require WX to be a second order constructive equation, then how is it that we can get a shear force out of it if we have to differentiate it 3 times?
So basically, in Euler-Bernoulli beam theory, if you use that, that's an excellent question. So the question being put.
Same question you was trying to ask before.
Oh, that was your question? I'm so sorry. I think I followed your question better then. So the approximation function, if it's second order, right, what's going to happen is, since it's Euler-Bernoulli beam theory, in Euler-Bernoulli beam theory, can somebody tell me what is the does the cross-section stay perpendicular to the neutral axis?
Yes.
Right? We talked about that. So the transverse shear is 0. The transverse shear stress is 0. And so if you use a quadratic polynomial, you have inconsistency. You'll get 0 shear. Okay? To get understanding of what the shear is, you'll have to construct integral. You have to integrate the equilibrium equations to get the shear distribution through the thickness of the part. Okay? But to answer your question, typically if you know the shear value, the value of shear, you can plug it in directly. In this case, you're right. If I were used to use a quadratic approximation, it will go away. It's not a great, you know, there is a gap there. And that's a great question. So if I have a shear load or something like that, then I think a cubic polynomial makes more sense. Not fourth order, which I was required before to have to impose, but a cubic polynomial. So that's a great question. All right, does everybody follow what just happened here? I've identified what is an essential boundary condition. I've identified what looks like a natural boundary condition, and I've noticed very, very quickly that these natural boundary conditions are actually physical quantities that we know what they are. We also know and realize that this deflection, if it's fixed, that is paired very quickly with shear. And then this rotation is paired very, very quickly with moment. Aren't these quantities that kind of, yeah, they go together in beam theory. The deflection goes with shear, and the rotation goes with moment. So it's coming out very naturally here. The second thing is that with weak form Galerkin, the natural boundary conditions are implicitly satisfied. You satisfy those implicitly. And so you have them here, and so you can plug their values directly. I'll go into that in a couple of examples so you can see how that works. And so the approximate solution to the problem, okay, the approximate solution to the problem you will see very soon are basically, they only have to satisfy the essential boundary condition. So not only have weakened the continuity requirements, now I only have to satisfy essential boundary conditions. In strong form Galerkin, the continuity requirements are higher. I have to satisfy essential and natural boundary conditions. In weak form Galerkin, the approximation function only has to satisfy essential boundary conditions, and the continuity requirements have halved. We divided that in two. Okay, so we have a little better situation.
Quick question. I don't understand how the basic function is equal to W with the arrow.
I'm not making it equal. I'm not making V equal to W. I'm trying to determine what is essential and what is natural. And to do that, you're going to pay attention to the V, to whatever has V in the boundary terms, and then you're going to switch it to W really quick to see, okay, anything specified on W is essential. And then you go here and say, okay, V prime, so if I make it W prime, anything specified on W prime is an essential boundary condition. So this really quickly tells you what is essential, okay? It's just a way to quickly tell what's essential boundary condition. Okay. All right. So moving forward here, what I'm going to do, I already showed you that these are moments and this is shear. And so since these are physical quantities that can relate to real life, I'll look at the beam problem. So this was a sign convention that I used, if you recall, to derive the beam equations. And so if I want to make everything consistent, I can take this here and substitute it so that everything's consistent in the same direction. So Q goes upwards instead of downwards. The moment is the same way here, yeah, sure. Here I want the moment to continue to go in this direction, counterclockwise. This one is the opposite direction. So I'm going to define some new conventions. And the purpose of that is when later on I discuss finite elements of beams, if I want to assemble systems of equations or approximate solutions for every single piece in the domain, it would be very convenient if everything was defined in the same direction. You agree? Right? And for that reason, I want to make this VL the opposite. Okay? And so here you can see I made the minus signs. I created some minus signs here. And so these are going to just basically correct that so everything's in the same direction. Okay? That's the goal there. And this can be actually mind-bending a little bit, but it does work out. Nothing to be concerned about. It does work out. It's mathematically correct. The whole idea is to have everything in the same direction and consistent. It just makes life easier later on when you assemble the differential equations together.
So Q is the same as the shear on the boundaries? Q1 or Q3?
So Q1 and Q3 will have the same sign convention. So I want to go, because W goes upwards for deformation, that's why I selected that direction to be the positive one. And also, if you remember, W prime, when I discussed W prime, the rotation was positive going this way. If you remember, the beam will deform like that, right? So I'm going to take counterclockwise to be positive, and that's why I'm reversing the signs, to be consistent with Q4. And I'm making this one here, Q3, to be consistent to Q1. And all you have is really a quick change here. So now everything in terms of Q, you can see here, everything's the same sign also, minus, minus, minus. Less confusion from that perspective. And then you have the Q's, which I've given in here. So if I substitute this here back in there, you get exactly what I had before in this equation. So nothing has really changed. I just used some different conventions here. And that's in preparation. I'm preparing you for the next step. The next step is finite elements of beams. At some point, we're going to do that. So I'm just preparing you to that step. And so now, to approximate solution to this partial differential equation, step 1, form the weighted residual. Step 2, weaken the continuity requirements. Step 3, select the approximation function. That's what we're going to do now. So I'm going to select the approximation function, and it looks like that. That's my approximate function I'm going to use. Phi sub 0 has the following properties. Only has to satisfy the non-homogeneous form of the boundary conditions. You're going to see that in examples. Phi has to satisfy only the homogeneous form of the essential boundary conditions. I will also give you some examples of that. But the bottom line is the approximation function I select, bottom line must satisfy the essential boundary conditions of the problem, if I have any. Okay. So then I'll go in and substitute this approximate solution into the weak form. And if I do that, and I select the V, this V right here, I selected to be each of the basis function, just like before, with strong form Galerkin. It's no different. It's the same approach. Okay? The only difference, I've weakened the continuity requirements by transferring two derivatives over. But at the end of the day, it's the same calculation. So if I have n basis functions and I have n c's, then I have n equations, don't I? Yeah? So then I can solve for the c's, for all the coefficients. Okay? And notice here that the fees are evaluated at the boundaries. These fees right here. Okay? In matrix notation, we can do this in matrix notation, which is a little bit quicker to see. I can write this in matrix notation in this manner. Okay, I'm looking for the unknown coefficients. And then I can go ahead and form the weak form. That's a weak form. But I can write it also in matrix notation. And in matrix notation, you can actually, it's just basically the same steps as we've discussed before. Okay. Matrix notation can be a little bit quicker if you want to have just doing one step. But if you're a little bit confused about the matrix notation, just do it in the long form. But both ways should work out. Both ways should work out, and I encourage you to try both ways because I think your understanding will increase significantly. Okay. Okay, so in the weak form Galerkin, the natural boundary conditions are implicitly considered in the weak form. We're going to consider them there. So in the weak form Galerkin, that's where we will substitute any natural boundary conditions. We'll consider them there. The approximate solution to the problem are the ones that will only satisfy the essential boundary conditions. As you saw, the smoothness requirements have been decreased for weak form Galerkin. We covered that one, and also we covered this one as well. So basically, each of your basis function must satisfy the homogeneous form of the essential boundary conditions. Okay. So we already kind of verbally walked you through these ones here. Okay. We've covered that in strong form Galerkin, but you want your approximation function to be differentiable, not to be discontinuous like that, because then you can't take that derivative. That won't be a problem for us because we'll be focusing in using polynomials for the most part. So let's see. An approximate function here was selected as quadratic, and if I plug it back here, is non-zero, so that's good. That's a good one to use. And somebody here had mentioned that, hey, wait a minute, my shear is going to go away. Well, if in that particular problem there's no shear, then maybe this is not a problem, right? But it is a deficiency if I use a quadratic polynomial. It's a great observation made in the audience. Very good observation. Now I will tell you this for beam theory. Euler-Bernoulli beam theory in abacus and by the formulation that's typically used, what is normally used is a cubic polynomial for the approximate solutions. So this won't be a problem. This question you have is not a problem because we'll be using cubic polynomials. But you do have a great point that using quadratic polynomial will have made that zero. This boundary term in here, the shear term. Okay. All right. Any questions? We're good. So the same rules apply. Complete set needs to be considered. Okay. The basis functions must be not just complete, but also independent from each other, linearly independent. Okay. So you cannot write the other two terms in terms of the third one, for example. And I gave you an example here of something that's linear dependent. If you do that, you'll get a singular stiffness matrix. It's not going to work out. Okay. All right, so I think the best way this works typically is with an example. I think it's the best way to illustrate. I gave you an example, of course, but it's with summation symbols. I think looking at it with actual numbers or examples can help. Okay, so example here is a case. Before I go to an example, actually, I want to cover something quick. So take this case here. This case is here. Phi sub 0 is 0. Right? Because in these cases, do you see anything here specified on W or W prime that's non-zero? No, so phi sub 0 is going to be 0 for those cases. In this column, what you see here is essential boundary conditions for which a non-zero value has been specified. In these cases, phi sub 0 is going to show up. Just to let you know. Okay? Okay, I'll get started now. So the question before we broke here is that the question I had here was, when is it 0? So this is 0 only when the essential boundary conditions of the problem, the essential boundary conditions of the problem, are homogeneous. And that means it's equal to 0. I'm prescribing 0 to the boundary condition. But when the essential boundary conditions have variables for which they have non-zero values, so like here, say, then in these cases, phi sub 0 is going to show up. Because that's the purpose of that. The phi sub 0 there is to satisfy those non-homogeneous boundary conditions, essential boundary conditions. Okay? Everybody's clear on that? And I want to make sure everybody understands too that each of the basis function must satisfy the essential form, homogeneous form of the boundary conditions. Okay, so if I have, as an example, so here, phi sub 0 would be non-zero for sure for a problem like this because W is an essential boundary condition and I'm specifying a deflection there, right? That makes sense. Okay. But phi, each of the phis here in this approximation theory, function, must be 0 at that value of W0. It must be 0 there, okay? Because it needs to satisfy the essential homogeneous form of that boundary condition that we're talking about. As an example, the one on the bottom here is W prime 0 equals alpha. Well, in this example, phi sub 0 is going to show up. It has to show up. And the basis function here must satisfy this essential boundary condition, but equal to 0. So phi prime 0 must be equal to 0. Is that clear? Okay. Very, very good. And there's another boundary condition here, by the way, which is W0. And this one is pin, so it's W0 equals 0. So it also has to satisfy that one. Two of them, right, in this example. All right, let's do an example. I think it works out. Example number 1A. I have like 6 examples. 1A is the first one. So 1A is pin with a distributed load. And in this example, the deflection is 0 here, of course. Is there any moments applied here? Any moments applied at either end? No moments applied. So EIW double prime is 0 at the ends. I'm not applying that. So therefore, W prime is 0 at either end. Okay? And you know, it's a physics problem. But if it's a mathematical problem, I'll have given you this. Hey, this is the equation that you need to know about, and these are the boundary conditions. That's it, right? But in a physics problem, you can actually interpret the problem and figure out what the boundary conditions are. Hopefully, you've taken mechanics of materials, and you can go back and review. So the idea here, what we want to do is determine the approximate solution using weak form Galerkin. So last week we solved this problem using strong form Galerkin. This week we're using weak form Galerkin. Okay, so the first step actually, before looking forward, next slides, what are the essential boundary conditions here? Sorry? All 4 are the essential boundary conditions? Just the first 2 are the essential boundary conditions. How do I know that? How do I know that these are the essential boundary conditions and not these ones? I will go to the weak form. I'll go to the weak form of the problem, which is right here. That was the weak form that we developed. And I'll focus here. I'll look at the V and the V prime. And this tells me if I put any values in W, and any values in W prime, these are going to be the essential boundary conditions. That's how you determine that. Okay? So in the example that we're talking about, we have values specified in W, and that's 0 in each of these. And then my approximation function only needs to satisfy these two, equal to 0. Not this, not necessary. Now I go in to developing those an approximation function. I select one. I select a quadratic one. Okay. And then, a form. I have to first find a form, how it needs to look like. I don't know how it looks. Because this one actually is not a good one, right? If I were to use this straight out, this would be wrong. Why? Sorry? The basis function here is not satisfying the essential homogeneous form of the boundary condition. For example, if I selected this approximation function, phi2 is not 0 at x equals L. And it needs to be because WL is 0. Right? It's giving me 1 actually. It's not giving me 0. So I know that this is not the way it looks like. But I need to start with this to kind of get an idea how it's going to look like at the end. And so I'll impose W at 0 is 0, and I get A0 is 0. WL, I will impose again, and I get A1 plus A2 is 0. So therefore, A1 in terms of A2 is the minus of that. If I substitute that back in, I get a form that looks like this. Well, this looks like a form that makes sense because this is your phi here, and this phi is actually 0 at x equals 0, and is 0 at x equals L. So this actually does work out, and I can actually add terms to it. I can add, this is not good. I don't know what happened there. But can you take a note there? Page 27. And so here, phi1 and phi2 are these guys right here. All right? And I can check it. You can actually check it, that these actually satisfy all the essential boundary conditions of the problem. How do I check that? Well, if you plug in x equals 0, I get 0 there and I get 0 here. That's great. It satisfies that. If I plug in x equals L, what happens? This is 0 and that's 0. That satisfies everything, 100%. But doesn't satisfy the natural boundary conditions. It's fine. I'm not supposed to satisfy those. I'm going to impose those in the weak form. Okay? And I'll show you how to do that. So I'll go back to the weak form. This was the weak form, remember? Okay? And I'll focus on these here, the boundary conditions. So each of the phis is 0, right? Because if I plug in L here, I get 0. So that's 0 for every single phi. And then here is also 0 because phi at 0 is 0. And you can see this goes away. These two go away really quickly, right? But here in this example, Q4, for example, is EI W double prime L equals 0. So didn't I say that W double prime was 0? W double prime was 0. So that's 0. So Q4 is 0 in this example. So you see how I imposed it into the weak form? I substituted this bond, the natural ones, I substituted in to the weak form directly. And so this one also, Q2, W double prime is 0. If you remember, these are the boundary conditions of the problem to remind you, right? And so that means that Q2 is also 0, and I'm making that 0. So all these terms actually go to 0, all of them. So the boundary terms in this example go away. You don't have to worry about it. Later on in other examples, that's not the case. So then I have two equations, two unknowns, and I have the phis, phi1, and I have the phi2. Remember, we chose the v's, the weight function, v, to be each of the basis functions. I have phi1 and phi2. Each of these v's have been selected as one of the basis functions. That's phi1 and that's phi2. So I have two equations, two unknowns. You can solve this, and it actually matches, it looks very close to the exact solution, okay? And the strong form, Galerkin. Let's move to the next example. The next example is 1b, example 1b, because it's this, kind of the same type of problem, but what I've done is modify a little bit for you. In this example, I have made it so that the rotation of this beam is 0, so it cannot rotate. But I made it so I apply a deflection of W0, just a little bit of deflection, just for fun. And then here I apply a load P at this end. And that's the kind of show you how to use this technique a little bit in a different way. And so the question here is determine an approximate solution to the differential equation. That's the question we have here. Okay. So again, we'll revisit the boundary conditions, looking at the boundary conditions of the problem. Just looking at the problem, you can quickly tell what is essential boundary condition. So in this case, the rotation is fixed. You agree? So W prime is 0. W prime is 0. That makes sense. And I also have another essential boundary condition because I'm specifying the deflection at this end. So that's also, and in this case, it's a value of W naught, right? I have a value there. Is there any other essential boundary conditions that you can see in this problem? There's nothing else. No other essential boundary conditions have been specified. For the natural boundary conditions, I can look here and you'll realize that since both of these are essential, there's no natural here. I don't have anything. I'm not applying a moment. I'm not applying a shear, right? A load. I'm not applying a load here. I'm applying a moment here. I'm applying a moment. Yes, actually, but it's 0. I'm applying moment equals 0, right? No moment. Okay? And that moment equals 0 means that EIW double prime is 0. That's what it means. Right? The other one I have is shear. I'm applying a shear load P, right? And it's acting in the opposite direction as Q3, the sign convention. So Q3 is minus P. Q3 is minus P. You got it there. Okay. Any questions on that? Any questions on that? Okay. You follow me so far? It looks easy. But if I leave you alone with a partial differential equation, and as I go and give me the unknown coefficients, and I go away from the room, I think there will be a little bit of a commotion. So I have 6 examples here. So you have a lot of examples to go by, and you're going to have a very beautiful homework. Very nice homework. Okay? Really fun. A lot of fun. Well, it is fun. It is fun. Just imagine you're solving the partial differential equation exact. You get the exact solution. Then you solve with methods that don't seem like they should work, but they work. Strong form Galerkin, weak form Galerkin, Ryder-Ritz. I'll show you the next one next week. And they all 3 match the exact solution. Isn't that great? Doesn't that give you confidence that finite elements should kind of work out? I think it will give you confidence moving forward. All right, so in this example, I'll take the approximate solution to the problem. I'll plug in 0 here to impose the first one, which is W naught. So here this goes away, and I have W naught equals W naught. What do I get there? I don't know what I did there. So yeah. So if I make W naught 0, right, then A naught equals W naught, basically. That's what you get. Then I take the first derivative of that, and I evaluate at 0, and set that equal to 0, right? And when you do that step, you find that A1 must be equal to 0, actually. So this term goes away, actually. That term goes away. And so then my approximation function actually just looks like this. As simple as that. So now I have the form. I have the form of how it should look like. I'll add another term. I can add more terms. I can go 4th, 5th, how many terms I want. The more terms I add, the closer I should get to the exact solution. Okay? In this case, for the purpose of this class, it will be very painful to do 3, 4, or 5 terms. But you can do that in the homework maybe, right? So 2 terms here. So let's see if this works out. So the first, after you come with your approximation function, I want you to check, does it satisfy the essential boundary conditions? Because in weak form Galerkin, the approximation function must satisfy what? The essential boundary conditions. In strong form Galerkin, it must satisfy what? All of them, essential and natural. You can already see how easier this is. Right? It's much easier. And so now let's check it. At x equals 0, what happens? I get the boundary condition that we talked about, W naught. At W prime, if I make this W prime and I evaluate it at x equals 0, this is going to work out, trust me. It's going to give you 0 also. So that's great. And notice how I have this term here, this extra term. This is what? Your phi 0. Remember I told you that if I specify a value that's non-zero on an essential boundary condition, this is going to show up. This phi 0 is going to show up. It showed up. Now remember, phi sub 0 is not a basis function. Its only purpose in life is to satisfy those kinds of boundary conditions. And here, this is phi 1 and that's phi 2. Okay? And I give you the phi 1 and phi 2 here to make it very clear what is phi 1 and phi 2. Now all we have to do is go into your differential equation. Sorry, your weak form. That's your weak form. And I'll plug in all the values. I have them all here. Okay? And I can plug them one by one. So let's go one by one. So phi JL, okay, what is phi JL? I think you can quickly notice, since every single phi is basically x over L squared and x over L cubed, if I put x equals L, what do I get there? Doesn't matter which phi I use. I get 1. So these are the phis. And actually I have the phis here. So phi 1 at L is 1. And actually phi 2 at L is also 1. You can check it. It works out. Let's look. Phi at 0 for basis function number 1. What does that give me? Sorry? 0. For basis function number 2? Also 0. So you can see here, I put 0 there and 1 for that. 1 for that. Let's look for phi prime there. Phi prime, I don't know anything about phi prime actually. I cannot do much with that. And then for phi prime 0, I have a problem here. Do I have a problem? No, I'm good. I'm good. I thought I had a problem here, but we're good. So phi prime at 0 is also 0. You can check it. So what is the derivative of xl squared? You will have an x, so this is going to give you 0. xl cubed, derivative of that, and then evaluate at 0, that's going to give you 0 also. So this is going to give you 0, this one right here. So that's 0, that's 0, and that's 0, okay? And that's 1. Doesn't matter which basis function. In this example, doesn't matter what basis function you use, you get 1. Now we need to look at the q's. We need to look at the q's. But we don't have to look at all the q's. Then 1 multiplies by 0, I don't care what the q is. So don't worry about that. That goes away. This one is also multiplied by 0, so don't worry about that q. Okay. This one has a q3, and we know already that a q3 we're applying a minus p, a load of minus p. So plug in the minus p directly in here. Do you see quickly that we're implicitly satisfying the natural boundary conditions by me plugging that in directly in there? Implicitly. Explicitly, we're satisfying the essential boundary conditions through the approximation function, but implicitly, we're satisfying that natural boundary condition. So I'm plugging that in directly, minus p. Is there a moment? Q4 specified? I'm not applying a moment. I'm applying a moment of value equals 0. Basically, I have no moment. And so moment equal to 0, that's your Q4. You can see here I put 0 there as well. So all these three terms go to 0, and I'm left with a plus p there. Just a plus p there. Okay? Any questions in what I just did there? There's a question in the back.
Well, I guess on the last slide, why do you start with a quadratic approximation, and then the next step you add a cubic term?
What I normally do to determine how the form of the approximation function looks like is I start with the minimum number of coefficients I need. So if I have 2 boundary conditions I need to satisfy, I usually use 3 terms. If I have 1 boundary condition I need to satisfy, I use 2 terms, and so forth. And the idea is that you can get a relationship of how these different terms relate to each other, so you can find the form that you need. That's how I typically do it. There's other ways that you can do it. You can do it by trial and error, but this is the way I do it. I try to use the minimum number of coefficients that I need to try to impose the boundary conditions. But I leave 1 open, so I can write it in terms of the other ones. Does that make sense? I think through examples you will learn more and more. Okay. Hopefully you can learn more and more on that. So then I have two equations, 2 unknowns, very quickly to solve. You can just do it in Mathematica. I did it by hand, but It's a great problem because this problem, you know the exact solution by not doing very much, actually. Anybody knows what is a cantilever beam? The deflection at the end of the cantilever beam for length L, load P? PL cubed over 3EI. Everybody here should at least memorize one thing, right? PL cubed over 3EI. Well, if you actually got the approximate solution at home, I didn't do it here, but I did at home, you do get PL cubed over 3EI, except not quite. You get PL cubed over 3EI minus W naught. Why? I moved the beam upwards W naught, right? So everything moved W naught a little bit. Then I apply a load P downwards, and so I get PL cubed over 3I minus W naught. Makes sense, doesn't it? So you can check your solutions to gain confidence in what you're doing. Okay. In this case, approximate solution matches perfectly the exact solution because I used basis functions that are also in the exact solution. They're common to the exact solution. And because of that, now I'm able to get the exact solution to the problem, which is great. Okay? Let's go to the next example. Actually, I did it here. I forgot about it. Yeah, I actually did it here in Mathematica, so you can see how I do it. So when you do your homework, you can actually kind of see how I did it. I actually did the approximate solution and exact in all, just these steps. That's it. That's all it took for me to do this. And so you can actually do this at home also in Mathematica. So here you can see I got W naught minus PL cubed over 3I. And the exact solution, if you make this x equals L, trust me, it gives you the same approximate solution. Okay? All right. Any questions? You have a question in the back, Christian? We're good? All right. So I'll continue here, right? So example problem number two. Problem number two. I resolved this with weak form Galerkin. So again, I have this partial differential equation. Here is very obvious what the essential boundary conditions are. It's fixed. So U is 0 and UL is 0. But assume for a second you don't know what the essential boundary conditions are. You don't know how to identify them. Okay, we'll talk about that. So I'll take this differential equation. What is the first step? I take the differential equation and do what with it? For weak form Galerkin. I'll first form the residual function, multiply by the weight function, and integrate it over the domain, 0 to L, in this case. And then I will weaken the continuity requirements. Those will be the steps. And so here in this example, I have the differential equation. I multiply by V, a weight function, V. This one has no derivatives, right? Don't worry about that one. This one has derivatives. I'll bring 1 over. I have 2 of them, split it in half. If I have 6 of them, put 3 over. In this case, I have only 2. I put 1 over on this side. So to do that, put the V on the left-hand side. I put the EAU prime on the right-hand side. And I'll reduce a prime over here. And I'll increase the order here to V prime. That's the step. Then I draw a line plus, minus. The one at the bottom goes inside the integral, and many people forget there's a negative sign, right? There's a minus times that. And then this plus PV, don't forget about that. Bring it back in. And then I have the boundary condition, which is these, the diagonal terms. This times that is that term. And there's an x equals 0 and an x equals L. That's the case. Now I want to know, say for a second, I did not know what the essential boundary conditions are. I know in this example because it's quite obvious. What will I do? Where will the focus be to find out? That V. I'll look at the V, the weight function. And then I'll look at the V and say, well, if I make the V U, which is the primary variable of interest, I make VU, if anything is specified on that U, then it's an essential boundary condition. Okay, that's how you find out, okay, what are the essential boundary conditions of the problem? Okay. In this example, I want you to notice also something really cool. Again, I start with a differential equation, and now I weaken the continuity requirements, and it turns out that these EAU primes have physical meaning. Isn't that what we discussed? This EAU prime is the load at the end, P? Yeah? If you don't remember, EAU prime is stress, isn't it? U prime is strain, right? What is E times strain? Stress. What is stress times area? Load. Doesn't it work out? It works out. It's incredible. When I first saw this, I said, how can this work out? But you will see on Thursday why it works out. Right now it's not clear why it works out, but it's okay. I'll show you. All right, and then here I have the boundary condition at x equals 0. Okay, so the weak form, and for convention I made a minus, so that both have the same sign, minus and minus. Okay, and then again, the weak form for this problem becomes this one here. Okay, you can still solve the problem with a plus here, and you can actually go and do all the calculations. It's going to work out. Don't worry about it. I made a minus so that when we derive to make the sign convention the same, so that when we derive the finite elements for a bar, we can use this approach. Okay. In this case, what are the boundary conditions for this bar? It's fixed on the left. It's fixed on the right. So u sub 0, u at 0 is 0, u at L is 0. Those are the boundary conditions of the problem. So the approximate solution I select must satisfy these boundary conditions. In this case, I already went through this before, and there's a problem with this again. We'll fix that. But you can see here, if I impose them, one more time, I have 2. How many boundary conditions I have? 2. I want to select an approximation function that has at least 3 unknown coefficients. Somebody asked me how do I do that? Well, I selected 3 in this case, and then I'll impose them. I'll impose them one by one, and then find out how the form should look like. And again, that's phi1, that's phi2, and this actually works out. At x equals 0, this is 0. At x equals L, that's 0. At x equals 0, that's 0. At x equals L, that's 0. So these are great basis functions. This is a great approximation function. It satisfies the continuity requirements. In this weak form, I'll substitute in for the weight function. I'll select the basis function, right? For u, I'll put the approximation function in there. So what I've done is substitute what u tilde is, which was given in the previous slide, which is quite, it's long. It's not short. And then boundary conditions become phi j at L and then phi j at 0. And so you can quickly notice that this will be 0 in this example, right? I can do it, but if I put this L and that 0 at each basis function, that goes to 0. You can check it. Phi1 at 0, 0. Phi1 at L, 1 minus 1, 0. Then I can do this one again. Phi2 at 0, that's 0. Phi2 at L is 0. And so in this example, these are 0. Okay? Any questions on that? So I want to also give you a little trick. We've done about 3 examples now. So I want you to notice something. That the phis have become 0 anytime I have an essential boundary condition. But that makes sense, right? Because we said that the basis function must satisfy the homogeneous form of the essential boundary condition. So anytime I have an essential boundary condition specified, I expect phi to go to 0 at that boundary, or phi prime, depending upon what you're looking at. Okay, so it does make sense. But anyway, this is what you get. And then when you plug in the equation, for phi j you put phi1, for phi j you put phi2. You have 2 equations, 2 unknowns, and again, awesome. Strong form Galerkin, weak form Galerkin. Strong form Galerkin was last week. Weak form Galerkin, and the exact solution was about 5 years ago when you took mechanics and material. And they all match very nicely. Look at that. All right, so next example, example 3. I'm going to tire you. I'm going to tire you with examples. I want to make sure you have enough examples, okay? So there's no excuses with the homework. So, not excuses. I know you guys try hard. So that's not what I meant. But so that you have enough examples to work it out, okay? I'm not going to bore you to death, but you take the partial differential equation. In this example, it's not a physical problem. So I gave you the boundary conditions. At u sub 0 is 1, u prime at 1 is 0, okay? So then I'll take the partial differential equation, construct the residual. I have the residual, make the residual orthogonal to the basis, to the weight function. And here, I'll focus and see I have two derivatives. My idea is to construct the weak form now, because I'm using weak form Galerkin. If I use a strong form Galerkin, I just stop right here with a strong form Galerkin. I don't have to go any further. But then if I stop there, and I use that, and I plug in an approximation function in there, the approximation function must satisfy essential and natural boundary conditions. With weak form Galerkin, I'm going to weaken the continuity requirements. Here, the only thing that has derivative is this guy right here, this term. So I'll put u double prime here on the right-hand side, v on the left-hand side, increase v by 1 prime, decrease u double prime by 1 prime, and then plus and minus. This goes back into the integral, as you see there, with a minus sign there. And then the rest goes in there, minus u times v, minus 1 times v. So please, many people do a lot of great things here. They do a great job there. These where they mess up. They forget about all these terms. It's easy to do. Okay, so if I was you, the first thing I will do, I write this first, v times u, v times 1, with the correct signs down here. Then do these terms next, if you don't want to forget. Okay, I'll be honest, I don't do it that way. I do this first. But I don't forget, because I've done this for a long time. Okay. And then I have the boundary conditions. I have v times u prime plus, all right, so v times u prime plus, and then 0 to L. And then how do I know what's the essential boundary condition? I already told you, focus on the v. Look at where v could show up, and v shows up here. Well, make that v u in your head. All right, so v is kind of like u. Well, do I have anything here that has u? Yeah, that's an essential boundary condition. Do I have anything else that has u? No, this is a prime, and that's not what the v has. V doesn't have any prime there. So this is the only essential boundary condition, and that's the only thing left, so that's natural boundary condition. Okay? So the approximate solution I select has to satisfy what? For weak form Galerkin? The essential boundary condition. So that's, I'll go ahead and select an approximate solution. Okay? Yeah, if you select an approximation function like that, you make x equals 0, you know, that x equals 0, a naught is 1, so that's what you get, a naught is 1. That's the only thing you have to satisfy, actually. So then you have this 1 plus c1x plus c2x squared. You can quickly see that I have this term here, this 1. That's your phi sub 0. Remember, I told you phi sub 0 satisfies a non-homogeneous form of the boundary conditions. That's exactly what happened in this example. Phi 1 is x, phi 2 is x squared, and then I can plug this in to the weak form. Okay? Any questions in what I did there? And then let's look at the boundary conditions. I just plug in for v, I put phi j, and then for u, anything you use, everywhere you saw u, I meant u tilde, basically. I already did some calculations here, so it doesn't look like I did it, but I did work it out. You can work it out at home, okay? Yes? Any questions? This is example 3. We have 3 more to go. You follow? Okay. But I'm not done yet. I'm going to plug in the natural boundary conditions. Here you will note that for phi 1, what was phi 1? X, right? So for phi 1 I have x, so that's why you see an x there and x there. I plug it in there for you. At x equals 1, x is 1, but u prime at x equals 1 is 0. I know that. That's a boundary term that gave you that information here. u1 prime is 0. So you can see that I impose a natural boundary condition and I plug it into the weak form directly. I plug this directly into the weak form. And then, so that goes away, right? And then here, I don't have to even do a lot. X equals 0, that goes away, clearly. So I have the first equation right there. Second equation, same thing. I don't want to repeat it. But you get two unknowns, and I did it at home again, and I got C1 and C2, the values for them. And then you can compare them. Weak form Galerkin and exact solution on top of each other. In fact, the strong form Galerkin also is on top of this, but I didn't plot it here. Okay? Yes? The exact solution has a bunch of e to the minus x. All kinds of complex, well, it's not complicated, but you have a lot of different things going on there, right? The polynomial solution got me, that's a really good agreement. Okay? With just a quadratic term, right? So you can see how weak form Galerkin is giving us a systematic approach. Not a very general approach, but for simple problems, it seems like it's working out, as you can see. It's working out. And I have these steps that are working out as well. Okay? Okay, so we have example number 4. Example number 4 is a typical homework problem that I give in a different course. Many of you may be familiar, those that suffered through that. But I solved it because I'm going to make sure they solve a new problem in this class because those people are here, actually. Here is the partial differential equation. At the edges of that square is a square domain. We're going to make the boundaries to be 0. So the value of u is 0 at the boundaries. That's what we're doing in this example. The exact solution is given here. How do I deal with that? So again, I take, don't get too nervous. It's not that hard. I take the differential equation. I construct the residual. Are you paying attention? I take the residual, make it orthogonal to the weight function. And now I have two derivatives here. I don't want that. I want to be able to split or reduce the order of differentiation from 2 to 1. And so to do that, I'll take this term and that term. Okay, this term is that one. And then the v on the left-hand side. And then I also have to multiply this by that. So I also have to do the same thing with this term. So v and that. So in this case, I'll reduce the order by 1. And for v, I'll increase the order by 1. Here, I'll increase by 1, and then reduce it by 1. So everybody follows that, right? Yes? And then I have a plus, and a minus, and a plus, and a minus. And you may notice this n. Okay? I'll talk about that. So this, will you agree that this is a 2D domain? This is a 2D domain. Yes? What is the boundary of a 2D domain? Sorry? What is if I have a rectangle, in this case, actually, in this example, it's a square. Well, that's a 2D domain I'm trying to solve for, right? In the 2D domain, what is the boundary of that problem? I'm actually have it right here. That's the boundary right there. It's a square. It's the edge, right? It's a closed curve, the closed curve. Because it's a closed curve, right? I need to know the normal of the curve at any given point in that boundary. Because of that, you're going to tag along an nx and an ny. This represents the normal at that surface, at that point, at that location. Okay? So here, I integrate it and I transfer an x over. You see that? Yes? Yep. So I'll make it nx. That's how you know that's nx. Here I transfer a y over, I made an ny. Okay? Everybody follows this. So if you have a 3D domain, you also have an NX and an NY. If you have a 3D domain, what is the boundary of a 3D domain? A surface. Excellent. In those two cases, 2D domain and 3D domain, the boundary terms are going to have this normal at the surface. Okay? In a 1D domain, what is a boundary there? It's just at x equals 0 or x equals x1 and x equals x2, right? Those are the locations that you're looking at. And so now I go, same procedure. Don't be nervous. It's the same procedure. So this times that goes back into an integral. This times that goes back into the integral. Plus, don't forget this forcing term, f0 times v, back in here. And then I have these boundary terms that look messy, but it's not that hard. What I've done here is multiply this times that and put them into the integral. You can see them right here. Okay, so I took that, and that's that term. And then this times that, that's that term. Okay, so all I've done is collect them together. And you can see here I have an integral, and that integral goes around the curve. Because, again, what is a boundary term of a 2D domain? It's a curve, closed curve. That's why you see that there. Now I took the curve and broke it up in two. One curve represents the edges where I put essential boundary conditions. And the remaining, if one edge is essential boundary condition, what is the rest? Natural. I mean, two options. Is either essential or natural. And I broke up the curve exactly like that. So I broke up one curve to be essential and one curve to be natural. Okay?
Can you explain again why you put integral part?
Sorry?
Can you explain again why you put surface integral on the boundary?
Because the question for the video is why did I put an integral in here? The reason is because you have a 2D domain, right? If I integrate by parts a 2D domain, what I get is a closed curve. So it's not a point value, right? It's an integral over that curve.
Yeah.
What I actually did here is Gauss' theorem or Green's theorem. If you took calculus, I just did it differently, integrating by parts. So you don't have to memorize it because some people have difficult time memorizing. So I'm showing you how to do it in a different way. Okay. And so what I've done, I've broken up the curve into two parts. One is essential, one is natural. Okay? And how do I know what are the essential boundary conditions of the problem? How do I check that? I already told you what to look for every single time. The V. I find out where V shows up. So in these boundary conditions, V shows up here, shows up here, shows up here, shows up here. Well, if I make V U, then I know anything specified on U must be an essential boundary condition. Anything that, if they tell you U is 1 at this part of the surface or curve, that is an essential boundary condition. That's how you know. It's by looking at these boundary terms. That tells you what that is. Okay? Any questions so far? Okay. Then I'll look and I'll realize in this problem, do you agree that the essential boundary conditions are basically all around the square? Yeah? I have no portion that's natural. Everything is like U is 0 all around. Doesn't matter where you look. So therefore, this term has been removed because I don't have any natural boundary conditions. I'm left with that. That's all I'm left with. And now all I have to do is substitute U for U approximation. And then for V, I select each of the basis functions, phi1, phi2, phi3, and I plug it in here. And that's basically my weak form Galerkin. Equation 1, 2, 3, 4, 5, n terms. And now look at this essential boundary condition, and I don't want to spend a lot of time because you know the answer. If I select a V to be phi, and phi has to satisfy the homogeneous form of the essential boundary conditions, and all the boundary conditions of the problem are essential, guess what happens to this term? Huh? If I told you already that phi has to be 0 at locations where essential boundary conditions are specified, and I already told you that all the boundary conditions of this problem all around this square is essential boundary condition, then phi is 0. And if you don't feel comfortable, leave it there. Doesn't matter. It's going to be 0 at the end. I'll show you that. Naturally. You can leave it there. and then worry about it later. Okay? So let's look at, this one is kind of hard for me to tell you, come up with an approximation function, so I give it to you. And that'll be the case in these examples. I'll give you the approximation function, so you don't have to suffer as much. And so this is a 2-term, and that's a 1-term. And you can check phi1 at the boundaries is 0, and phi2 is also 0 at the boundaries. You can check it. All around the square, it will be 0. So therefore, this phi1 and when it's phi2 will be 0. You will check, and it's going to work out. Okay, so I took that, and I plug it into Mathematica again, weak form Galerkin. Very few steps, actually, you can see, just one. All the steps I took from here to here, that's just for 1-term approximation. You can see very few equations to get the answer. Okay, and then here you can see very few terms to get an answer for 2 terms. And this actually matches Strom from Galerkin. And it matches, and it's within 0.5% of the exact solution. It's great. 0.5% of the exact solution. Okay, so 1D heat transfer, there's a question in the back.
Why did you multiply by the nx and then y in the
Yeah, so if you use the Gauss's theorem, you will see that you have to multiply by a normal when you go from a volume integral to a curve that encloses a surface. Here, the explanation I gave you was a little bit different in that if I have a closed surface, right, I need to know where I am in that curve, right? And I need to evaluate that against the normal at that point in the curve, right? So that's why we're doing that here. Okay.
So ds right here means
ds is the differential length along the curve. Okay. In this case, it's a square, right? So ds is a straight, basically along a straight line, and you can go around. In this case, there's 0. So it makes our life easier. In a 1D heat transfer problem, if this is the equation, again, multiplied by the weight function. In this case, I use W, just to throw you off a little bit. It's not always V. You can just use W. So multiply by the heat conduction, the residual function. In this case, it's this one. If you integrate by parts, you get the weak form. I'm not doing this for you. I'm just giving you the answer. So that's 5A. You have one problem to practice right here. And that's 10 points extra credit for Thursday if you do this. If you show me that you get this weak form. Okay? And there's potentially, I will not tell you whether this is true or not. It's possible there's an error here. But it may or may not be true. Okay? So if you're looking for the slide number, that's slide number 50. If you're looking for that. 5B, example 5B, there's another heat transfer problem, but it's a conduction-convection problem. Conduction and convection problem. Again, multiply by form a residual function, that's this one here. Make it orthogonal to the weight function. That's your weighted residual. Integrate by parts so you can weaken the continuity requirements. Here you don't have any derivatives, so don't worry about it. And then now you have your weak form. And again, 10 points extra credit by Thursday if you can make this work. And there may or may not be an error again here. Okay. Okay. Last example. This one is a little bit tough, but it's not that tough because I think it's a simple it's a concept that can be followed. It's systematic. In this example problem, I have 2 equations. I'm giving you 2 differential equations. Okay, 2 differential equations, and I have 4 boundary conditions. How do I deal with that? How do I do that? How do I even implement weak form Galerkin? Well, I already showed you how to deal with 2 equations with strong form Galerkin. In this example, I'm showing you how to deal with this problem with 2 equations, but now using weak form Galerkin. Same steps. I form the residual function with this equation, and then the residual function with this equation. So for equation number 1 times V1, that's my weight function. Equation number 2 times V2, That's my second equation. So I have two weighted residuals, and equations up to this point in time. I have 12 minutes to go through these examples. So are you following?
Are V1 and V2
V1 and V2 are weight functions.
are they related?
They're not. These V1 and V2 are independent weight functions from each other. They're not related. V1 is for this equation, and then V2 is for this equation. Yes? Excellent. Any questions? Okay. What is the next step? I don't want to even tell you what the next step is, because I think everybody here knows what I'm trying to do. If I am using a strong form Galerkin, this is where I stop. But then I have to choose approximation functions. They're at least quadratic. They satisfy essential and natural boundary conditions, right? And they have to be complete and has, everything else, right? But with weak form Galerkin, what do I need to do now? Reduce the order of differentiation. So I want to learn these terms. Weaken the continuity requirements from second order to first order. And I'm split it in half. If I have a fourth order, I go down to second order. Okay? Yes?
Yep.
And the approximation function only needs to satisfy the essential boundary condition, unlike strong form Galerkin, where it satisfies both essential and natural boundary conditions. So let me integrate by parts, because you guys love this. I take this one here, multiply by V1. Here I have a differentiation. I could shift it over, but why? I cannot really split the order differentiation from 1 to half. That's probably the best I can do. So you don't have to do any more there. Just leave it alone. And you can see these terms, I just wrote them down just like they are. I didn't do anything with them. This term, I shifted 1 over to V1. And you can see here how I did it. Decrease the order by 1. For V1, increase the order by 1. Plus, minus, bring this inside the integral. Repeat for equation 2. For equation 2, you can see here I brought it back in there just like you see. And then for the first term, reduce the order by 1. For V2, increase the order by 1. Plus, minus, bring it back into the integral. And then I have the boundary terms. Okay? Then how do I know what are the essential boundary conditions? So I look at where V shows up, in this case V1, and then I have a V2 here. So if I make V1, what is the essential boundary condition? Since the first equation is dominated by what variable? The first equation is dominated by what variable? What is the dominant term in the first governing equation? That's the governing equation from here to here. What is the dominant term? C. Because C has the highest order differentiation. Here, W has the order of highest differentiation. So V1 is related to C. V2 is related to W. That's how you have to think about it. So V1 in this case, if I were to specify anything on C, the variable C, that will make it an essential boundary condition. Here at the bottom, V2 is related to W, right? And here V2 shows up. So therefore, anything specified on W becomes an essential boundary condition for the second equation. Something to make very clear, if I had another term that showed up for integration by parts that said V2 prime, say, V2 prime, then anything specified in W prime also becomes an essential boundary condition. But in this example, this is all you have to worry about, right? Okay, so these are the essential boundary conditions. Anything on C, on anything on W. So now I continue, and from now on it's the same steps. Same steps. We enforce the essential boundary conditions. In this case, I gave you the boundary conditions, so you can plug them in. So that for the first equation, you can quickly see that C prime at L is 0. So that's 0. So that's a natural boundary condition. Because we said that anything on C and W is essential, so everything else is natural. So plug in anything that's natural in directly, and you can see that's 0. Okay? So don't worry about looking at what this is for x equals L. Don't worry about it. It's gone. No worries. This one here, we know that at x equals 0, v is like psi, right? This v1 is a psi. And I have a psi of 0 equals 0. So this is 0, right? That goes also away. For equation 2, the same story. In this case, both of these are 0. Okay? Both of these are 0. At x equals 0 and x equals 0 because w is 0 at each of those boundaries. And the v's are weight functions that are selected as the basis functions that satisfy the homogeneous form of the boundary condition. So expect those to go away. So then we seek an approximation of this form, just like before. And for this psi this way. Okay? So we have two approximation functions. For the first one, I have to figure out the form of that. Since w has to be 0 at x equals 0 and 0 at x equals L. I'm not going to go through the steps. I think I bore you to death with the same approximation function. You know, at the end, you get this. This is your approximation function. And you can see that these phis satisfy the homogeneous form of the boundary conditions. For psi, I chose an approximation form that looked like that. The only boundary I need to satisfy psi at 0 equals 0 because that's the only essential boundary condition. And again, the approximation functions only need to satisfy the essential form. I don't have to worry about the natural. The naturals, I just plug them back in directly into the weak form. That's how I satisfy them. So in this case, the form looks like this. A1xl plus A2xl squared. Okay? Then we have two equations, two weak forms, one with V1, one with V2, right? And we know that V1 goes with C and V2 goes with W. So when I plug in the approximation functions, I have to be careful. For V1, since it goes with C, I want to select the basis functions to be the ones that go with the ones for C. So for C is lambda 1 and lambda 2. So I'm going to select for V1 lambda 1 for V1, and then for V1 lambda 2, and that's my two equations. In the right-hand side, you see the two equations for V2. I selected it to be Phi1 and Phi2 because that goes with W. And for W, I have Phi1 and Phi2, if you go back. Phi1 and Phi2. And so then you can solve. I actually did it, but I didn't want to write it out. It's four equations, four unknowns. You can see here quickly that all the lambdas are known. All the phis are known. The only unknowns are A1, A2, C1, and C2. Four equations, four unknown. You can solve them fairly quickly. Does that make sense? So let's summarize what we've done with the weak form Galerkin. The weak form Galerkin is an approximation method that it is what it forms. I mean, it's basically what it forms the basis for finite elements. Okay, in strong form Galerkin, we're one step removed. With weak form Galerkin, we're basically there. So if you learn this method, I think we'll be in good shape. And I see some people in the back excited about it. The weak form Galerkin, what we've done is weakened the continuity requirements. That's why it's called weak form. We took the strong form Galerkin, basically a strong form formulation, and from there we integrated by parts. Then we select an approximation function that satisfies the essential boundary conditions. The natural boundary conditions, which is the remaining of them, I basically substituted those directly into the boundary conditions of the weak form. That's why I satisfied those. And I gave you about 6 or maybe 8 examples actually, because I had 1A, 1B, and so forth. So you have plenty of examples to look at. And I think if you follow these examples and you follow the strong form Galerkin from last week, and with what I'll teach on Thursday, that you should be able to do fine in the homework, okay? All right, so with that said, thank you very much, and I'll see you Thursday.